So hello everyone. So welcome you all to the ninth problem solving session for the NPTEL course titled Multirate Digital Signal Processing. Myself Saurashis Chatterjee, PhD scholar from IIT Kanpur, and today we are going to solve a few problems based on the content of lectures from week 9. So before that, let us revisit the contents of this week's lecture in a brief manner. So first crucial thing we have observed that incorporation of Multirate-DSP framework for multi-carrier modulation. And when I say multi-carrier modulation, I also I mean it OFDM also. Will often use the term OFDM and multi-carrier modulation interchangeably, which is not exactly wrong, because anyway OFDM was previously known as multi-carrier modulation, and the uh, multi-carrier modulation is the fundamental, the building block of the OFDM, and of course it's the main driving force behind its prominence. So let us write first. So first we have seen incorporation of multirate DSP framework in multi-carrier modulation. Second thing we encountered, our professor discussed in a very elaborate manner about the M channel uh, transmultiplexer transreceiver framework, actually M channel transreceiver, and this brings back a few of the earlier concepts discussed in the lecture from earlier weeks of these filter banks. Of course, these are filter banks are the building block of this course, and they will appear again and again. That we have seen the synthesis filter and analysis filter in context of this M channel transceiver for multi-carrier modulation. So let me write it down here. Filter banks, synthesis filter, analysis filter. Actually we are going to solve problem on each one of them, so I'm just high upsample at the transmitter side and downsample at receiver side for the condition for estimation. We'll see that all. And the third important things we have seen, the quite important concept of redundancy. uh, you can also see in terms of error correction. Like in error correction you have this parity bits, that is the actually you can also call them redundant bits, because they are not actually, their purpose is they are not used on purpose for data transmission. Suppose you have a fixed block length and your message length is less than that, So the rest of the bits are filled up with these parity bits, but of course they are actually used to make the communication more robust for error correction purpose. So here we encountered this concept of redundancy uh, through the framework of this multirate DSP, and we'll solve a problem also on that, and if possible we'll see somewhat what exactly happening and why redundancy is important, and especially in practical scenario. So with these things in mind, let us move to our first problem. So first problem is regarding a question of water filling algorithm. So it asks that whether water filling can be performed in frequency domain or time domain, or both in frequency domain and time domain, or none of the above. If you have gone through the lectures, you know that water filling can be performed in both frequency and time domain, but I think beyond answering this question, I should explain in little bit some way that how water filling is necessary in both the domain. Professor of course has elaborately discussed the necessity of how water filling is done over time and frequency, and what are their conditions, or why this is performed. I just feel to kind of repeat that discussion in my own words, of course, because this water filling concept is a very crucial concept. It actually allows you to allocate power based on your channel condition over both time and frequency to achieve optimal throughput. So yeah, it's worthy of revision. So for that, as done in lecture, I will kind of write this flowchart thing. We divide it into three parts: that water filling over time, water filling over frequency, and water filling over both time and frequency. So when you do water filling over time, this is basically you assume your channel to be of frequency flat. So based on your observation, or compared to the signal bandwidth, the channel bandwidth is higher, therefore the channel appears to flat in frequency domain for your region of work, and this is time varying, and this become important for fast fading channels where channel really varies over time. So you must keep your pace with the channel condition and keep allocating power optimally to achieve the maximum rate. Otherwise your performance or achievable throughput is going to be suboptimal if you don't do that. So this is happen when channel is frequency flat, time varying. That means basically it is varying over time but not over frequency. Second, I think this one over frequency, which I guess is discussed in most water filling algorithm discussion, is this one, that over frequency allocation of optimal power. And this is because your channel becomes frequency selective. What does frequency selective mean? You can have intuition by now that basically your channel gain is not going to be constant over the entire bandwidth, right? Entire bandwidth of operation. So channel gain is going to vary across the frequency. So that is what the reason behind the term frequency selective is, because it means it selectively amplify the signal based on its frequency region, maybe for some frequency it is going to amplify your signal, or for some frequency it's going to deteriorate that. So like that only. And this is for time invariant channel. However, practically what you observe, your channel is varying across both time and frequency, so that necessitates the allocation of optimal power over time and frequency. That means your channel is frequency selective and time varying. Let me briefly discuss that what do you mean by like time varying channel. Just an example. Time varying channel. Classical example would be fast fading. That is channel. In fast fading channel characteristics, and by the way, channel characteristics, channel gain, this kind of terms all leads to the to represent the channel gain, which is our main concern here, because water filling algorithm allocate power, as you can remember from our previous session discussion also, solely on the gain of the different channels. And what is the principle we have seen? The strongest channel, it assign the highest power. So you can consider it to be a greedy algorithm in that sense also. So for fast fading channel.
Sir, please, I have some question I want to ask, if you don't mind.
Yeah, sure.
Sir, actually my question is from the like class note, sir.
Okay.
Sir, actually sir मैं class loss understand कर रहा था. Sir, you are like, अच्छा please see here. Sir, you are able to see here, sir.
Yeah, I think, yeah, like not very
Now
clear.
clear?
Yeah, fine. Okay.
Yes. सो सर ये उन्होंने अपने क्या कहते हैं क्लास नोट्स में एक्सप्लेन किया था ये वाला पार्ट कि अगर अगर ऐसे होता है तो सर एक्चुअली ये है इसके अबाउट, इट इज अबाउट द लाइक पॉलीफेज डिकम्पोजिशन सर.
Okay.
And sir, in it I have to like achieve the means I have to achieve the complexity by 6 times. I have to achieve the d complexity by 6 times. So in it we have 2 steps, 2 approaches.
Okay.
In it approach he told that if अगर मैं ये और इसको किया जाए एक साथ में अटैच कंबाइंड, so that I can so that मैं अचीव कर सकता हूँ 3x lower
complexity, right?
Complexity and
Okay.
and if I attach here मेरे को मिलेगा 2x lower complexity सर.
Okay.
सर फिर उसके बाद मेरे को ये वाला स्टेप एकदम ही अंडरस्टैंड नहीं हुआ सर. यहाँ से फ्रॉम हियर आई कैन नॉट अंडरस्टैंड लाइक अच्छा ये स्लाइड्स हुआ कैसे सर. एक्चुअली इट वाज इन द लाइक 5th sir, it was in the week number 5.
Okay, week number
where
5.
He was explained. Yes, sir. Week number 5.
Okay.
First lecture. Sir, I am really very sorry.
No.
I have
It's
stopped you.
see, that's my goal, na, like to clear your doubts. But the thing
Yes,
is,
sir, this is my doubt.
Yeah, so I need to.
So sir, आपका अभी जो भी हो रहा है लाइक मेरे को उसके आफ्टरवर्ड का चाहिए टाइम सर, so that I can interact you on the Google Meet and like clear my all the class note doubts. Sir, I want to say that sir मेरे एक्चुअली स्पाइन कोड का इंजरी हुआ था, तो सर आई एम अभी मेरा अच्छा अच्छा माय सर। अच्छा अच्छा सर, अभी मेरा सेकेंड ईयर है फ्रॉम द इंस्टीट्यूट लाइक। अच्छा 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 अच्छा, आईआईटी बॉम्बे सर। आईआईटी बॉम्बे से सर मेरा अभी वायरलेस कम्युनिकेशन के अंदर 2 इयर्स का अच्छा अच्छा एमटेक है सर। और सर ये वाला कोर्स मैंने एज ए अपना क्या कहते हैं क्रेडिट कोर्स लिया है सर।
Okay,
तो आई नीड
okay,
क्लेरिफाई माई ऑल द डाउट, सो प्लीज गिव मी द टाइम ऑन योर लाइक गूगल मीट
okay,
आफ्टर
okay.
सेशन।
Sure, sure. After
So
session,
sir,
so like,
so I need your like mail ID where I can drop, or I can share my mail ID for asking the question, sir. I need help. Please
yes.
share me your mail ID, sir.
So I am sharing my mail ID in the comment box as of now. You can copy it. Just a minute.
Sir, you can like share me here in the like message. You can share, sir, please, so that
Yes,
I
yes.
can
That message only I am
ask you
giving.
the things,
Yeah, sure,
clarify my all doubts.
sure. Just a minute.
Yes. Sir, actually I am having a bit of stammering problem, and also sir मेरा है ना स्लिप डिस्क का इशू हो गया था, तो सर अभी
Okay.
मुझे आना पड़ा था अच्छा हॉस्टल छोड़ के अपने क्या कहते हैं मम्मी पापा के साथ।
अच्छा,
सो
अच्छा,
सो ये कोर्स मुझे, हाँ ये कोर्स मुझे यहाँ से फिनिश करना है अच्छा अच्छा एनपीटीएल से।
अच्छा. No,
अभी
I
थोड़ा ठीक
understand.
हुआ है मेरा पेन, अभी थोड़ा पेन ठीक हुआ है। आई कैन चेयर इन द सिट और आई कैन नॉट सिट।
Okay.
यस सर।
No,
थैंक यू
मतलब
सो मच फॉर अंडरस्टैंडिंग माय प्रॉब्लम सर।
no issue, no issue. That's my job only. So I think today I am not sure that whether I will be have a session with you or not, but tomorrow definitely. Okay. And please
Yes, sir. Tomorrow
let
we'll plan.
and one more thing, since this is the content from previous weeks, so I need to revisit them once. So can you please
Voice is broken. Yes, sir. Yes, sir.
so you can hear it now.
हाँ हाँ, please say again.
Okay,
I missed.
so I am saying that whatever doubts like the specific problems na, you can just
Yes, sir.
take a screenshot,
Screenshot.
yeah, a screenshot,
And that.
and drop me a mail like that, so that I
Yes, sir.
can like revisit them. And that, because I need to revisit the concepts also, because since it's
Sure,
from
sir.
week 5,
Sure.
and
Yes,
then
sir. Week
I
five.
can make you understand. Then like I will try my best to do that. Okay.
थैंक यू सो मच सर।
Okay,
थैंक यू
okay,
सो मच
sure.
सर।
I didn't no issues.
सर
And
सर
yeah.
अभी मैं ये जो है आपका सेशन छोड़ रहा हूँ, बिकॉज आई हैव फिनिश माय प्रीवियस वीडियो लेक्चर्स। और सर मैं आपसे जो भी क्वेश्चन है वो मेल पे कर दूंगा, एंड सर थोड़ा सा आपसे हेल्प लेता रहूंगा
Oh,
लाइक
no
शाम को
issues, no
6 बजे के बाद में
Sure,
सर।
sure, sure. No issues. Sure,
थैंक यू सो मच
sure,
सर। थैंक
sure,
यू सो
sure.
मच फॉर द सपोर्ट
And
सर।
please don't call me sir. Just address me by my name. That's more than enough. Like sir is really
सॉरी।
embarrassing.
ओके ओके सॉरी, आई विल स्पीक बाय द नेम एंड इट विल बी अ ग्रेट ऑनर फॉर मी टू वर्क विद यू सर। सो मैं आपको जो भी मेरे को शेयर कर दूंगा ऑन योर मेल आईडी द स्क्रीनशॉट्स व्हिच क्वेश्चन आई एम नॉट एबल टू अंडरस्टैंड द approach or like concept, I will share on that thing.
Okay, okay.
I will
Just
ask to you sir.
okay. Yeah, sure, 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 sure,
Thank you so much for your time.
sure.
Now I want to leave it, please actually don't mind, I have to finish week
No, no,
5,
no,
week
no,
6,
no.
week
I don't
7,
mind
week
at all. I don't mind at all. Sure,
एंड
sure, sure,
मैं थोड़ा हेल्प लेता रहूंगा आपसे प्लीज।
sure, sure, sure,
जी जी
sure.
जी सर। जी सॉरी। थैंक यू फॉर
So
दिस टाइम, थैंक
okay,
यू सो
okay,
मच।
sure.
ओके, थैंक यू सो मच प्लीज।
uh, okay, so let us start from where we are there. Okay, we are discussing time varying channel. So a classical example, or the best way to understand a fast fading channel, where the channel characteristics really varies fast over time. So it's like, if you just in a crude sense, if I try to make you understand, it's like this. uh, Suppose this is channel, and this is your G, which is nothing but channel gain. So it's like and this is the uh, time axis. So you can see the channel gain here really varies fast over time. So if you don't allocate your power optimally at different instants, you are going to achieve suboptimal performance. So this corresponds to time fast varying channel, where channel characteristics varies, or let me write it, changes okay. So this is channel. And another kind of is where you see frequency selective channel. So as the name suggests, your channel gain is changing over frequency. If I want to draw it, your channel in frequency spectrum, which you denote as h of f, and this is frequency axis. So see, a channel is frequency selective also depend on your region of operation. Suppose you are only concerned with this portion of channel, this bandwidth. Okay, so for you it can be frequency flat channel, correct, for your region of operation. But suppose your region of operation or the bandwidth is this. Now let me write it down with a different ink here. So just let me point it out with this. So if your region of operation of this, or you are concerned about the behavior of channel in frequency domain over this spectrum, the denoted by these green lines. So for you or your operation, region of operation, this is frequency selective channel, correct, because the gain here value of hf and the gain hf value here are not the same, they are dependent on the frequency. However, if your region of operation or the bandwidth portion you need is only this much, so for this you can consider your channel to be frequency flat. So the main idea is behind that only, that suppose you have a channel, sorry, you have a signal xt that you pass through channel h t and you get output yt. So given a LTI system and their respective Fourier transform being xf, hf, yf. For LTI system, your yf is going to be just multiplication of xf times hf, correct? If your signal bandwidth b is, so let me write it down here, xf bandwidth of xf is b, or bandwidth of hf concern is bc. This is not a correct way to write, let me know, okay, and write it like here, hf, or the frequency spectrum of the channel, is frequency flat over bandwidth bc. Now your signal bandwidth b is greater than bc, what will happen? You will see frequency selective distortion, like you will see distortion in your signal outside the frequency flat portion, correct? So channel becomes frequency selective. Because like consider this frequency flat over bc. Now if your signal bandwidth b goes beyond bc, it is going to observe distortion. So channel for your region of operation based on your input signal bandwidth is going to be frequency selective. On the other hand, if your signal bandwidth b is less than bc, you can approximate the channel as a frequency flat channel. So since you general practical channel for a particularly for a wideband input signal, you are going to have both frequency selective and time varying nature of channel. It's very crucial to allocate power optimally via opti water filling algorithm, and water filling can be performed in both frequency and time domain, and we'll see in the next slide how it is done. For this, let me draw this diagram. The diagram is also taken from the lectures only, but I think it's worth revising the diagram again to fully understand its capability or the reasoning why we have to perform water filling algorithm over time and frequency domain to achieve maximum throughput. So since this is a 2D screen, but I need a 3D 3 axis, so I am denoting the third axis with a different color which goes inside the page. So please consider the current purple line I am drawing, it's going inside the page, and this axis represents channel gain, and this axis here, the purple color line, it represents time t, and this here is the frequency axis. So if you take a 2D intersection, like at every time, any time point, like suppose this is a point, you consider this point here, you consider it to be t is equal to t naught, you consider some point here which is t equal to t1, this point here. So you will observe the channel behavior across at different points of time, and at every point how water filling algorithm is going to optimally allocate power for a frequency selective channel, where the channel gain is different over different frequency, like over different bands. If you try to relate this to a OFDM scenario, OFDM basically what you do, you divide your wideband signal into narrow subcarriers, and the corresponding channel gain you also see, and the channel bandwidth is also divided into this sub-channels, and these sub-channels have different channel gain based on their frequency. The characteristics of frequency selective channel. So the main advantage is that even if one subcarrier the channel gain is pretty low, the other subcarriers which observe good channel gain can still reliably achieve or continuing the communication, therefore achieve better performance, other than if you let the entire channel to carry your signal. If the channel experiences very bad condition, then your overall communication is going to fail. So idea is to divide your channel over narrow band sub channels which can carry informations. Now let's get back to our discussion on water filling algorithm. So this point here, just for your understanding, it is t is equal to t1. So let's look at t is equal to t0. We denote the heights, different heights, to represent different channel gain here. So first channel gain, first sub channel gain is this is first sub channel. The second sub channel consider having quite higher gain to that. The third one is lower, fourth one is slightly higher, fifth one good, sixth one very bad. So we have seen the optimal power allocation. How did water filling algorithm works? It basically have a optimal threshold value, if you remember from the previous live session, and of course from previous lectures also. So if the channel gain is beyond that level, only then it is going to allocate power, and otherwise it is not. So for our discussion, let us consider this is the optimal level, threshold level, and let us index this sub channel also, like this is first, this is second, third, fourth, fifth, sixth. Okay, so by the water filling algorithm principle, you see here the third channel gain is below the optimal threshold, so it is not going to allocate any power to this channel. The same happen for sixth channel. So these two channels are they are going to discard, so they will assign power between this fourth channel only out of six of them. Okay, and this is the channel condition you observe at t is equal to t naught. Suppose at t is equal to t1 for a time varying and frequency selective channel, like a different instant, your channel condition is going to change. And let us see compared to if we consider t is equal to t naught case, you will see the your first channel is going to observe a better condition, I would say. Second channel, which is pretty high here, among like the channel gain is this is the best channel condition, comes down. The third channel, which was discarded in the previous instant, like barred from allocated any optimal power, is have the best channel gain at t is equal to t1 instant. Fourth channel gain, which is allocated power in the previous instant, but at t is equal to t1, it is like this, and then on like this. So suppose for this channel, like for you observe channel t is equal to t1 over different frequency beans. By the way, beans I mean the sub channels only, and across different frequency bands. And let us index them here also, 1 2 3 4 5. Okay, we are supposed to draw one more here. Fine, and let me join them to better compare it with. The drawing is a pretty bad quality, so please forgive that. I hope I am able to make you understand. It's just the joining is for the purpose of comparison between two t naught and t1 instant, for better visualization only. Okay, not a very good representation, but still. And another thing, let us consider the optimal threshold for the channel here is this. So let us check which of the channel are going to be discarded. Second one we are going to discard, the fourth one, the fifth one, and sixth somehow get pass. So you can see from here to here the channel condition and your corresponding optimal power allocation changes rapidly. Why is that I'm saying? You see the second sub channel, which turns out to be having the best channel condition at t is equal to t naught instant, and according to optimal power allocation strategy of water filling algorithm, it's going to allocate maximum power to this. You observe the channel at t is equal to t1 instant, where the second channel second sub channel gain is even unable to cross the optimal threshold. Therefore the sub channel is not assigned any power. So the sub channel which has been allocated maximal power in the t is equal to t naught instant by water filling algorithm at t is equal to t1 instant, for this example has been assigned no power at all. So you can see, you have seen the optimal power allocation of our frequency band before. We have across different frequency bands which represent different sub channels of our frequency band. Of course, then they are based on the different channel gain, you are assigning them power. But across the time, it is very important to perform this optimal power allocation using water filling algorithm, because if you don't do that, consider for t is equal to t1 instant, it is going to assign no power to the third channel in spite of having best uh, channel gain, correct? If we maintain the same threshold here to here, so they are not going to assign, like their decision is like they won't assign any power to third channel because it has decided not to do that. But at t is equal to t1 instant, the third sub channel has the best channel gain, and it will assign maximum power to the second sub channel, which actually at t is equal to t1 has very low channel gain. So this is a suboptimal power allocation that will drastically reduce your performance. So that is why it's very important to allocate like use water filling algorithm in the time domain also. In the frequency domain, the comparison is relatively much easier. You can see in frequency domain, different sub channels at different frequency bands are going to observe different channel gains. Based on that, any particular time instant, you are going to allocate them power. So that is the context. So you can say this is water filling at t is equal to t1, which is substantially different from water filling at t is equal to t naught. So the idea is, at a given time instant, you have to perform water filling across different frequency. In context of OFDM, different frequency corresponds to different narrow sub channels. So they are the, you can use them in the interchangeable way based on the context, of course. And at different time instances, what should be your goal? You have to repeat the water filling across frequencies. Therefore, as we have discussed on before, the water filling can be performed in both frequency and time domain, and it's a necessity more than being can or can be in a practical scenario, of course. Okay, just a minute. I hope I am audible enough. Okay, with that, let us move to our second question. It concerns about a single carrier system with 10 microsecond RMS delay spread, and the bandwidth is given as 4 MHz. The system uses QPSK modulation with MLSE decoding. By the way, MLSE refers to maximum likelihood sequential estimation. And Viterbi algorithm, what will be the order of complexity of the decoding? If you refer to the lecture directly, you have seen the order of complexity of decoding. You can write as m to the power l, where l is the number of symbols of inter-symbol interference, that is ISI, and correspondingly, of course, you can, if you see from the perspective of channel modeling, it's l plus 1 tap channel. Why L plus 1? Because there are L symbols of that causing interference, but there is also one desired signal which you are supposed to get via means of equalization, but the goal ideal is to mitigate all the interference from other symbols. So as the number of delay taps increases, or the number of symbols in the ISI increases, you can see the order of complexity increases, because mathematically it is m to the power l. So if l increases, the complexity increases faster compared to increase in m. By the way, m is the constellation size you are going to use for your modulation. So whether it's a BPSK or QPSK, or it's a QAM, whatever you use, if your constellation size also gets bigger, then it's the order of complexity of decoding really becomes very significantly high. So here there is a concept of RMS delay spread. RMS delay spread concept is a little bit complex, so I'll talk briefly about delay spread only here. So it's good enough for you know about the RMS delay spread, that it is nothing but weighted combination of delays. By the way, for weighted combination of delays, you need to understand the channel delaying model. It is nothing but like this. You have this transmitter, you have this receiver, there is a LOS channel, there is a building here, and there is a tree here. Okay, so when you transmit something from the transmitter here, uh, actually the signal received via three paths at the receiver end. One is this path, this corresponds to delay of tau naught, this corresponds to delay of tau 1, and this corresponds to a delay of, let's consider, tau 2. So your corresponding channel model, you can write something like this: ai del t minus tau I runs from 0 to 2. Correct? Is nothing but, if you have drawn, this is something called channel delay profile. Channel delay profile for a A0, A1, A2, tau naught, tau 1, tau 2. So it's nothing but this is the, since the path looks the smallest, so it arrives at a delay of tau naught where the channel gain is A0. This one, reflected by a far located object, traverses a larger path, therefore reaches the receiver at a delay tau 1, which is greater than tau naught when the channel gain is A1, and the signal receives at a larger located tree and traverses a larger path compared to this tau naught and tau 1 corresponding paths, therefore reaches the receiver at a delay tau 2, which is greater than tau naught to tau 2. So delay spread corresponds to time when these multiple copies of transmit signal received over different time instant at receiver. So this duration is also called like maximum delay spread, and this actually causes your inter-symbol interference, because suppose you are transmitting multiple symbols. So what is that? When does your problem starts happening? When your symbol duration becomes comparable to the delay spread. If you use high bandwidth signal, that corresponds to your signal symbol duration is going to be low. Correct? Now symbol duration low means the difference between two signals, back to back signals, are going to be low. So when that happens and your signal, this symbol bandwidth become comparable to the delay spread, what is going to happen? You transmit a symbol, you receive that receiver, you perform decoding. When you receive the second symbol via this path, there is a good probability that the copy of the first symbol is reaching also at the same time at the receiver. So you are going to observe inter-symbol interference. Correct? Suppose via this path you have received first symbol, you have decoded it, fine. When it's time to receive your second second symbol, what happens when your delay spread and signal symbol duration becomes comparable is that a copy of the first symbol is going to interfere with that, and the higher your delay spread becomes, there is a very good chance there are the multiple copies of previous symbol are going to cause interference to your present symbol. That is called inter-symbol interference, and which is a severe problem in wireless communication. So I hope I am able to make you understand about the concept of delay spread. It's not beyond the scope of this particular course, but I think since there are a few questions related to delay spread, a brief idea about delay spread will help you understand what is happening. Basically, for a wideband signal, for a very high bandwidth signal, your symbol duration is going to be low, and when symbol duration is going to be low and it's comparable to the delay spread of the channel in consideration, then it is going to causing interference, like current symbol is going to be interfered with by the multiple copies of previously sent symbols, therefore causing intersymbol interference. And the goal of this multi-carrier modulation technique OFDM is to mitigate the ISI to the large extent, and ideally mitigate completely. That is it. So back to our question. The RMS delay spread, RMS delay spread given as sigma tau is 10 microsecond. Your signal bandwidth is given as 4 megahertz. The constellation used for modulation is QPSK, that is quadrature phase shift king. Let me draw a small constellation diagram for QPSK. Basically, the constellation diagram consists of 4 points referring to total of 4 symbols: 1 1, 0 1, 0 0, 1 0. So since there are 4 symbols, how many bits you can transmit per symbols? It is basically log base 2m. So by the way, QPSK means m is equal to 4 symbols. So how many bits you can transmit per symbol? Essentially, if the number of symbols in the constellation becomes high, you can transmit more number of bits per symbol. So for BPSK, where you have only 2 symbols, that is -1 and +1, of course corresponds to phases pi and minus pi, you are going to have log base 2 to only 1. So for BPSK, per symbol you can transmit 1 bits of information. For QPSK, where the symbol number is 4, you can transmit log base 2 4, that is 2 bits for information, which is evident from this here. You can transmit 0 1 1 1 0 1 not 4 combinations. For 4 QAM also same, you have 4 symbols, so you can again send log base 2 4, that is 2 bits of information. Take 16 QAM, you transmit log base to 16, that is 4 bits of information. Similarly, for higher, like 64 QAM, you can transmit 6 bits of information per symbol. But they also require the channel condition to be very good. So but effectively your SNR should be quite high, so that both transmitter and receiver can handle that high modulation, like basically decoding capability. Your SINR should be high for correct decoding of higher modulation, and of course you can achieve higher rate. So let me write down the full form of MLAC here for the reference. It's maximum likelihood sequential estimation. Correct? So let us point the order of decoding complexity, which is given as m to the power l, where m is equal to number of symbols in constellation. L is the number of symbols of ISI, and you can say it's also number no, L is not exactly number of L plus 1 is the number of delay taps. That is a part of channel model. So for this question, what is the L? So L is the number of symbols of ISI, or where L plus 1 is the number of delay taps, where L number of symbols corresponds to interference and 1 corresponds to the desired symbol. So L is obtained by let us write number of taps here, L plus 1. The formula is that is L plus 1 is equal to RMS delay spread divided by symbol duration. So by the way, let me write here the symbol duration also. Symbol duration actually your signal bandwidth is given, so it's easy to find symbol duration, which we denote as TS is nothing but 1 over B, and B is a signal bandwidth, 1 over B second, so it results into 4 megahertz. That is you're going to have 0.25 microsecond if I need to write it in unit properly. Actually the case is more severe when symbol duration gets lesser and lesser compared to delay spread. The situation becomes like more severe because you are going to observe more and more number of copies of previous symbols from this channel delay model I just now explained. So if your symbol duration is even lower, as the symbol duration becomes lower than your delay spreads, the inter-symbol interference become more and more severe, and then your corresponding equalization process. Equalization means basically you want to obtain the process of obtaining the desired symbol without ideally without any interference, or in practical scenario largely removing this interference, is become more and more complex, so your complexity increases. I think we'll encounter somewhat this kind of problem in the next slide or something. So okay, let us first write this one. This is 0.25 microsecond. So therefore RMS delay spread is 10 microsecond. Your symbol duration is 0.25 microsecond. It becomes 40. So that means your L is equal to 39. Therefore your order of complexity, you can write m to the power L, that is 4 to the power 39. By the way, when solving this question, this is a elaborate thing. Of course, in exam you need not do that. You need to just remember m to the power L. But be careful about this part, that L is not equal to RMS delay spread over symbol duration, but rather L plus 1. Because if you write here L, you will get L is equal to 40, and you will be tempted to choose the fourth one as the correct, which is not at all. So when solving this objective kind of question, you must remember the mathematical formulas very like this is important, where the number of taps of channel is equal to RMS delay spread over symbol duration. So please remember it in accurate manner, that is it is equal to L plus 1, not L. So you obtain order of complexity as 4 to the power 39. With that, let us move to our third question, where we consider two systems A and B, where A is a 21 tap channel and 16 QAM modulation, and B is a 51 tap channel with QPSK modulation. So we have seen previously that order of complexity depends on both M and L, and so increasing M and increasing L. M is the constellation size of modulation, and L is the number of delay taps of channel, or from point of intersymbol interference you can consider number of symbols of intersymbol interference. Therefore you can view this question as a find the exact trade-off between M and L. So one system A has 21 tap channel, that is L values is relatively less than the B system have 51 tap, but it is going to use a higher modulation technique, that is constellation size is 16 QAM, so its M value is higher compared to B, which uses only QPSK modulation. So it's the question is really appropriate manners form, that you can vary the value of M and L in different direction. You can say that which of the system prevails over another in terms of complexity. Generally the complexities, we want complexities to be lower for implementation point of view, of course. And both the scheme are said to use MLSE decoding with the Viterbi algorithm, so that thing remains same. So for system A, (21) tap channel, how can we write it? It is L plus 1 is equal to 21, correct? And 16 QAM modulation. That is your constellation size is equal to 16, or in other sense 16 symbols are available for this particular kind of modulation. So L, which represents number of symbols of ISI. You can also see that if L plus 1 is equal to the number of taps, that is L previous symbols in a sequential orders, their copies are going to interfere. So that's also a nice way to visualize things. So you obtain from this L as 20, and from this we obtain M as 16. By the way, M is equal to 16 means you per symbol you can transmit log base 2m bits per second, that is 4 bits per symbol you can transmit, and that is a really higher level of modulation technique. You need to have quite good SNR value to uh, communicate using this modulation technique. That is your the effective channel between transmitter and receiver should be able to support this higher modulation technique, because it's not about what you are transmitting. Your receiver should be able to capable of demodulating it, and for being capable of demodulating it, your channel condition should be good enough. So that's a two-way thing, not only transmitters decision. The thing is how it happens. Basically, the user, when it connects to a base station and at a certain frequency of intervals, it feedbacks its channel condition to the base station, that okay, I am having this kind of strength in channel or that kind of strength in channel. And suppose like base station user feedback that okay, now at this instant I have 10 dB strong channel, or a certain instant I have a 20 dB, or at a certain instant I have only minus 5 dB. These are not real values, just to give you an example. So based on that information, base station decide which of the modulation technique it is going to use to transmit data to that particular user. So that is the goal. If you have seeing a very good channel, your channel condition is very good, then base station is going to use a higher modulation rate. And as you see from these examples again and again, higher modulation rate means basically you are able to transmit more number of bits per symbol, so therefore your achievable rate is going to be very high. So that is the principle behind like seeing all these um, 180p resolution or 2K or 4K videos. They are basically possible when your channel strength is really high, and whenever your channel strength drops, you are not able to see it because channel cannot support that high level of data rate. So it must move to lower modulation technique, where you can transmit less number of bits per symbol, but at least the communication will be reliable. So yeah, think I am moving out of context, so let me have the discussion to me. Okay, so for this system A, the order of complexity is nothing but m to the power L, that is 16 to the power 20. You can write it as 4 squared times 20 also, that is 4 to the power 40. For system B, it's a 51 tap channel and Q PSK modulation. So therefore constellation size is only 4, that is you have 4 symbols to choose from. So you obtain L plus 1 like previous case is equal to 51. That implies L, which is number of symbols of ISI is 50. For your order of complexity becomes m to the power L, m value is 4, so 4 to the power excuse me. Okay, let us denote the complexity of system A as CA, complexity order, and this is C2. Now we can observe that CA is 4 to the power 40, the order of complexity, whereas C2 is 4 to the power 50. Therefore we see C2 is greater than C1. Therefore we observe system B has higher complexity. One important point to remember here, that although this question concerned about the trade-off of two system A and B, it is not for this particular question. It might seems that when number of taps are higher or number of symbols of ISI is higher compared to uh, between two system, even if the other system use higher modulation technique, it would need lesser complexity compared to the channel which has higher number of delay taps. But please don't take that as a generalized thing. That will vary case to case, and that is solely dependent on m to the power L. For different choice of m and L, it can well appear that modulation techniques sometimes can cause more complexity even if the channel taps are less. So it can happen both ways. That will vary on case to case, and single-handedly neither m or L is going to define the order of complexity in a complete manner. You need to look at m to the power L, the order of complexity, to fully understand or to fully capture the orders of complexity for a particular system. So we see that system B has higher complexity, therefore the answer is second one. With that, let us move to our next question, which says in a there are two statements given. Statement 1 says in a multi-carrier system, low complexity equalization can be implemented over each subchannel. And statement 2 says that as the signal bandwidth decreases, the number of symbols of ISI decreases. By the way, whenever we repeating this term again and again, number of symbols of ISI, it basically means for a particular delay spread, value of a channel and a particular signal input signal bandwidth, how many uh, previous copies of symbol, not copies exactly, uh, how many previous copies of symbols, how many previous symbols are going to interfere with your current symbol. The more number of copies are going to interfere, the more severe is going to be your case. So basically we have to find whether the first job is to find whether the statement 1 and statement 2 are correct, and the next job to find whether statement 2 is correct explanation or not, and statement 1 and statement 2 can be both false also. So let us move to statement 1. So it says that in a multi-carrier system, low complexity equalization can be implemented over each subchannel. It is actually true, and also this statement is the fundamental behind this popularity of OFDM, that it achieves the same only, that in multi-carrier system low complexity equalization can be implemented over each subchannel. That is how OFDM achieves that. It breaks down your channel into narrowband sub-channel, so that it can employ low complexity equalization technique, and you can transmit your data on these multiple subcarriers parallelly without causing interference with each other. That's the concept of OFDM. So that's correct only. And how can we achieve that? We have already previously seen that I have mentioned that if your signal duration is lower, the in degree of severity of ISI is higher, correct? So if you are somehow able to reduce the bandwidth of each subchannel, this decrease in bandwidth, it corresponds to increase in symbol duration. Now if your symbol duration increases compared to your delay spread, then therefore two signals arriving with a very small time gap are going to be negligible, so there is not going to be any interference, and you are able to employ low complexity equalization over that. That is the goal. And statement 2 says that as the signal bandwidth decreases, the number of symbols of ISI decreases, and that's true only. Because see, low complexity for statement 1, if you say, it says that low complexity equalization can be implemented over each subchannel. Now if your signal bandwidth decreases, your symbol duration increases. Correct. So if symbol duration increases, there will be lesser and lesser symbols of ISI causing interference, that is your L value is going to be less. So therefore the complexity of equalizer, which is decoded by m to the power L becomes less, therefore your equalization becomes low. So the complexity of equalization becomes low, that we employ over each subchannel. So without wasting time, let us explain in a more detailed manner how it happens. So consider a wideband signal with bandwidth B. Now it is divided into narrow band signals, each of bandwidth b dash, which is b over n. Correct. Now this corresponding symbol duration, how much is that? This t was 1 over b. Now for this case, if you divide this wideband signal into several narrowband n narrowband signals, that is number of n narrowband signals, each of bandwidth b dash b over n, then your corresponding symbol duration becomes t dash is equal to 1 over b dash, which is nothing but n over b, which is n over t. So what you observe from the case we just mentioned, multi-carrier system, what you do, you divide wideband signal into several narrowband signal and transmit them over narrowband subchannels. So how does it help? You can just see that symbol duration increases from t to nt for a multi-carrier system. Correct. Now we know number of symbols of ISI Okay, we observed number of symbols of ISI is equal to RMS delay spread over symbol duration. So you can see when a symbol duration increases from t to nt, and for a large enough n, when you divide your wideband signal into this n narrowband signals, what you basically do, you increases the individual signal bandwidth and you increases the symbol duration n times. So So therefore your RMS delay spread of the channel remains fixed, because that is the property of channel, that remain fixed, but your symbol duration become n times. So therefore your number of symbols of ISI for this particular example, number of symbols of ISI decreases n times. Correct? And it is denoted by L. Therefore we can write the corresponding L as sigma tau over B, and this one for this wideband signal case, when signal is not divided, for single carrier case, sigma tau is the RMS delay spread, and this is symbol duration T. Therefore their number of symbols of ISI is L is equal to sigma tau over T for this case. For this case, single carrier. For multi-carrier case, however, this case your T dash becomes n times T, so therefore your L dash becomes sigma tau over T dash. Correct? Therefore your L dash is n times less than L. The order of complexity earlier was m to the power L for multi-carrier case. It becomes m to the power L dash, that is m to the power L over n. Therefore order of complexity decreases. Correct? So we have seen this, how the decrease in signal bandwidth corresponds to increase in symbol duration, which causes number of symbols of ISI to decrease, and number of symbols of ISI that corresponds to which is L, is nothing but which directly related to the complexity of equalizer, which is given as m to the power L. So as the number of symbols of ISI L decreases, the complexity becomes m to the power L by n when signal is divided into n narrowband subchannel. Therefore the equalization complexity reduces, which we can implement over each subchannel for a multi-carrier system. Therefore statement 2 is a correct explanation for system 1. So first option is the correct one. I am mentioning again, you have a wideband signal, you divide into many narrowband signals, therefore you decrease your signal bandwidth. It causes increase in your symbol duration. Increase in symbol duration causes number of symbols of ISI to decrease. Number of symbols of ISI is also number of delay taps. I mean, not exactly, it is L and L plus 1 anyway. but the equalizer complexity is given as m to the power l, where l is the number of number of symbols of ISI. So the equalizer complexity becomes m to the power l over n, which is a very low complexity compared to the earlier case, and you can employ this equalizer over each subchannel for a multi-carrier system. Therefore, statement 2 is the correct explanation for statement 1. With that, we move to our next problem. It's actually regarding the interesting concept of redundancy. So let me just briefly revisit the contents of regarding redundancy in the uh, lecture. So you have lecture, you must remember this these things, this transmultiplexer, where we combine all symbols before all the signals before transmission. So you are feeding all these spectrums here. One spectrum is like this, another maybe like this, another one maybe like this. So this transmultiplexer, which is supposed to generate a signal whose frequency spectrum is given by this. There are n such as, and this is a ideal scenario, but in practice this is ideal scenario of the frequency spectrum of them are non-overlapping, but there is also no gap between them. So if there is some quality problem in transmultiplexer, or in practically it's really not achievable sometimes. So what you want a guard band between these different spectrums to be able to correct, so that they do not overlap with each other. So therefore what happens in practical scenario, you introduce the concept of guard bands. This is upsampling by m, and here you actually do upsampling by n, which is greater than m. Just a minute, it should be m here. You're combining m's different spectrums. So here what you do, you introduce and these things you call guard bands. By sampling at a slightly higher rate compared to number of channels. So for this example, you see it's a 100 channel multi-carrier, sorry, 1000 channel multi-carrier system with 10 nanosecond symbol period and QPSK modulation, and the system uses the upsampling factor of 1024. So therefore you have number of sub channels 1000. So therefore ideally the upsampler with the upsampling factor of 1000 would be fine, but to have these guard bands which act as a margin also, you upsample with the upsampling factor of 1024. This is M here, this is N. This N minus M 24 redundant samples. This results into 24 redundant samples, and we want to know what is the transmission throughput rate. So the symbol period TS is given as 10 into 10 to the power minus 9 second. Ideal case, which corresponding to without any redundant samples, your transmission throughput rate is given by B over TS. So let me introduce B here. B is the number of bits per symbol for QPSK. Constellation size is 4, that is we have 4 symbols to choose from, and using these 4 symbols you can transmit log base 2 4, that is 2 bits of information per symbol. So therefore, for ideal case without redundant samples, you have 2 over 10 into 10 to the power, sorry, I'm writing wrong here, 10 into 10 to the power minus 9, that is 200 MB Mbps transmission throughput rate. But for our example, with redundancy, as in our example, redundancy. Since all the bits are not going to be used for data transmission, there are 24 redundant, all the symbols are not going to be used for transmission purpose solely only. So that is for this case, all these symbols are not going to be used solely on purpose of transmission, but there are 24 redundant samples every 1024 samples. Therefore, with redundancy, your actual throughput rate is given by m over n times b by ts, that is 1000 over 1024 into 200 mbps, which results into 195.3 mbps. Therefore, for our question, the second one is the correct answer. Next, we proceed to the structure of M-channel transceiver. We have seen in this structure in lectures. We have this M-1 parallel input signals that effectively passes through filter bank, which we are calling transmitting filters, and this resulting output was subsequently added to form xn. Therefore, this entire transmitting filter bank is also, you can see, as a synthesis filter bank, because we are synthesizing all these input signals S0n up to Sm-n to form xn, and then it passes through this channel Cz, noise is added, and then again it passes through a receive filter bank H0 of z up to Hm minus z. After some downsampling, we obtain S0 hat of n, which is estimate of S0 n. You can see this is, let me write it down here. You can synthesis filters, because you are synthesizing all these signals, combining all these signals to form xn, whereas at receiving side, what you are doing, you are analyzing different parts of the signals that you have received. You are passing through them different filters and analyzing this spectrum analyzing the behavior at different spectrums. So therefore, in Multirate-DSP framework, this you can term as analysis filters, because you are passing your input signal through different filters to study their behavior across different spectrums. So this filter bank here consists of analysis filters, and ideally in context of OFDM, what you want, that S0 of hat of n should depends on S0 of n only and not other signals. That is, there should not be any symbol interference present. So the question asks, the wideband signal xn, the combined or synthesized signal xn, is given by what? So you can see, let me, in the intermediate step, let me denote them as V0 of n, V1 of n, of 2 V m minus 1 of n. So xn, you can see all this u0, u1, um minus n are added to form xn. So xn we can already visualize from the diagram only. It's a summation of uk of n, where k runs from 0 to m minus 1. So this part is also correct, but there is another option which says that both 1 and 2 can be correct. So we need to check whether xn can be written in terms of input signals and the corresponding channels. So let us see that. By the way, the channel CZ here, it should be represented as FZ, and if we take it's, you can see it's a LTI system at the end of the day. Therefore, if we take the Z transform, we get Fn. Sorry, I'm taking the wrong one. I'm not interested in the channel part here. Sorry about that. Okay. So these filters F0 Z, F1 of Z, Fm minus Z, these are LTI filters. So therefore, the input-output relation, we'll see that after a minute. But first we will consider the inverse Z transform of a filter, generalized filter Fk of Z. If you take inverse Z transform, you are going to obtain Fk of n, where your k varies from 0 to m minus 1. Okay, and if we consider the intermediate sequence to be vmk minus 1, let us consider this particular step. Consider one of this signal, you take skn generalized version, you pass through a upsampling factor of capital M, we obtain vk of n, we pass this through this filter, synthesis filter fm minus 1 z, and we obtain uk of n. Correct? And since sorry, it should be fk minus z. fkz. Now corresponding impulse response of this, since this is a LTI system, corresponding impulse response we get as fk of n. Correct? This is the discrete time impulse response. So how this input vkn and output ukn related? Via this, for this LTI system, we know that ukn is going to be convolution of vkn convoluted with fkn. Correct? The property of convolution operation, what we can write, vkm, where m runs from minus infinity to infinity, fk times n minus m. Correct? Now you observe this particular block where vkn is obtained by upsampling skn by a factor of m. So therefore we can write vkn as follows, where vkn equal to sk n by m for n is equal to 0 plus minus m plus minus 2m, like that, and 0 otherwise. Correct? This is upsampling property. So from then you can observe this vkm. If you consider these two equations 1 and 2, you can see if m here is not a multiple of capital M, m here is not a multiple of capital M, it is going to have a value of 0. Correct? So we can write the same thing here, m runs from minus infinity to infinity, and also one thing, m is multiple of m fkn minus m. Correct? Because for all m which are not multiple of m, bkm is going to be 0 according to this property. So we are fine. Now we consider m is equal to L times m. We are considering without loss of generality since m is a multiple of m, and as m tends to infinity, L tends to infinity, m tends to minus infinity, L tends to minus infinity. Correct? From this we get this. So this we can write as, we change the index from capital M to capital L, Vk Lm Fk n minus Lm. Correct? Now Vk Lm, can you write that from this too? We can see Vkn is Skn over m for n multiple of m. Since Lm is a multiple of m, Vk of Lm is nothing but L tends to minus infinity to infinity Sk of L. Fk expression remains same, n minus Lm. Correct? If you see, does this expression matches with this one here? It does, right now? Because what is the expression here? We obtain ukn as L is equal to minus infinity to infinity skl fk n minus Lm. Therefore xn, from this equation we can write, just replace ukn by this expression here, we'll get this k is equal to 0 to m minus 1 summation over L. We are not mentioning minus infinity to infinity, or we can, it's same only, skl fk n minus Lm. So therefore this one is also correct. So x can be expressed either this way or can this way. Therefore both first and second option are correct. So therefore the correct option should be third. Okay, with that we end today's session. We'll again meet on next Tuesday regarding the contents of lectures from week 10. Thank you all.